what is the condition on K? Okay. No, that's right. That's right. But before that, my question was that is there any condition on these coefficients? So the coefficient, what are the conditions? That's right. And are there any other conditions? Okay. And K also has a similar expansion. Okay. So maybe I will write S here. Okay. That's fine. That's a good way to say actually that both have same power. Okay. All right. Okay. And then what is the question? So and choose K. And choose K equal to B naught, choose C naught. Uh, okay, I'll just write a dot. Okay. B1, choose C1. Okay. Till BR, choose CR. And modulo anything? Modulo P. Okay. Yes. So yeah, Aditya has just joined. So I'll just say the question. So this is apparently what Vaishnavi is saying. This is apparently called the Lucas theorem. I don't know. I mean, I have not done this before. Lucas theorem. And the problem says to prove this using Silo theorem, maybe Lucas's theorem. And the Vaishnavi, is that correct? We want to use Silo theorem to solve this, or okay, okay, group actions. So let's think. I don't have much idea, but I suspect that maybe let's assume for the moment that this is also like this. Okay, I suppose we can all understand the why I'm doing this. I mean, it means that okay, I am doing this because this then means that it's a unique expansion of base P expansion, right? If you don't put that condition, then it is not a unique expansion. Yeah. So I'm just putting that. I mean, maybe then we can remove that condition and still solve the problem. Let's try it. So these are the digits basically. These are the digits. And yeah, P is a prime. No. Yeah, I understand maybe why you're saying that, but that is not necessary. Uh, unless Vaishnavi, is it given in the question that BI is less than CI? Sorry, yeah. Is it given the Ci is less than Pi? No. Right. So in that case, what we should interpret, then it is zero. If so, I mean, that's a natural extension. So 2 choose 4 is 0. We will interpret it like that. And it is fine because if you just take the definition, if you take the polynomial definition of choose, that it is n and then n minus 1 and then n minus 2, n minus 3 by 4 factorial. If I take this definition, it actually comes out to be 0. Right? So usually in the literature, we have to do this. I mean, usually we have to sometimes do this to say things in a uniform way. Otherwise, you have to say case one this mod p or case two zero mod p. Right? Two questions. It will become two questions. Yeah, it is not true if p is not a prime. That I was just checking by doing modulo 10. This is a very Okay, group actions. What should we act on what? Is this so? Have we checked it for small things and seen it is true, or I we should believe it is true, but so you see, I mean, if all the BIs, if okay, I realize it's not going to be very useful. But if all the BIs are at least CI, I mean, right, then that implies that RHS is not 0 mod P, right? Because none of the factors will have a divisor of P, right? Because of this. And in that case, yeah, but it doesn't contradict anything, of course. In that case, LHS is also not 0 mod P. Seen identities like this means these divisibility identities. But Okay, so does anyone remember there was a formula for VPN factorial in terms of base P expansion? What is it? There is, right? There is a very slick formula. Let's try to imagine. Let's take some small cases and see. You will get some nice. Because of course, in general, we of course know this. Whatever it goes, I mean, not iron, but whatever goes on actually, and it's actually yeah. There's no factorial here, of course. So what will it become in terms of the expansion? This formula, this one. Yeah, no, so you just means they just see that it is true, right? Because n factorial, okay, it has a name. It is called de Polignac's formula or whoever's formula. But n factorial, so you want to count the so the highest power of p that divides n factorial, right? So you want to basically know how many numbers from 1 to n are divisible by p. That is this, right? But then those which are divisible by p square, they will contribute one extra. So you also add them, the extra contribution of them. And those which are divisible by p cube, they have even one more extra contribution which you have not counted in any of these, right? So that's n by p cube and so on. I'm just give you a rough, I think. Okay? You can prove this. This is a very useful and nice formula. But maybe if you also don't know this, then you just prove this later, okay? Yeah. But can we now use this to maybe I'm just distracting ourselves from the actual question, but I mean, it's just I see something a little bit. So maybe, so I mean, we can just look up the formula, but let's think. Can we use this and a base P expansion to get a nicer formula? Imagine this. Okay, let's take this as a black box and you see, I also don't know, but I'm just working my way up to it. Sorry. So you have to add these things, right? I'm just writing this n by p here. This is n by p floor. This is there will be a beautiful formula if we combine this nicely. I think I see it. N minus sum of the digits of n base p by p minus 1, right? It looks like that, right? So this is the formula. Let's quickly check this for a small case and then take it as a black box, right? Let's take n equal to 10. Let's expand it, maybe base. I am using this theorem, yes. Is that the theorem you are referring to? Uh, yes, I'm using this theorem to get another formula. Yeah, so I use this theorem and then I'm using this theorem. I'm using this theorem and using this base P expansion, right? Then I'm writing like this, okay? And then because I can just calculate, so I know that it's going to be this. Okay, but it's not a deep fact, so we can just take it as a black box. But just let's check it for a small case. Is that fine? Okay. Yeah. So now let's just check this. SPN is sum of the digit space because you can see it's kind of like that. If you add the partial geometric progressions and so on. Expand this base 2. Let's do that. What is it base 2? 2 cube. Right? So n is equal to 10. And what is sum of the digit space 2? 2. 2 minus 1 is 1. So it is 8. Now let's match. 10 factorial may how many powers of 2 are there? 2, then there is 4, right? And then from 6 you get an extra 2, from 8 you get 8. So how much is this? 1, 2, 1, 3. Sorry, and then from 10 you get one more. Nice, this is 8. Okay, so the formula is correct. We can prove it later if you, yeah, you should prove it. Maybe you will find a different, more elegant proof than this. Yeah. Okay. All these formulas will have names of ancient mathematicians, but I think remembering names is more difficult. So, yeah, now if I use this here, okay, I'll just let you people think. Okay, if I have to say something useful, then I will say. Yes, I have something to say. So you see, if this condition is matched, then you see uh, this thing is 0. Why? Because these are like if you do periodic, then yes, yes. Yeah, you can. Why don't we can black box this? No, it's fine. You think you can? Yeah. Oh yes, yes, yeah. Sorry, the notation was floor. Yeah, yeah. I should didn't say that. Yeah, floor. Mhm. SP, sum of the digits base P. I also didn't say that. Yeah, sum of the digits base P. Basically, B naught, B1 till BR. Okay. Yeah. So this is like n and then yeah, the polynomial evaluated at 1. So yeah, so this is like if you have p-adics integers which are actually integers, then this is their expansion, And if they are not integers, if they come after the completion, then you get an infinite expansion. So maybe there also some of this may lift, and you can make some interesting comments about the geometry and so on. Should do. So of course, we have this. This is true. And this is because we know, is it fine? This, it's a, if you like, it's a valuation. It's a map from Z cross to, yeah. So yeah, Z cross to R, here it's N. Anyway, so this thing, and what do I want to say? Yes. So you see, it's a this formula beautifully tells you that this is also 0. Why? Because if you use the formula, you see, you get SPN by P minus 1, which is, it kind of sits outside quietly. Very nice. Okay, I'll write SPN there, but I'll write this here. It is sum of the digits. Just take the most natural interpretation, right? Sum of the digits. If it was something more fancy, I would say. Okay. Okay. So SPN is sum of the digits, and of course in base P. So if don't say something, it means that it's something easy only. That's why I'm not saying. But okay. So then it is this, and again, I'm writing all this, but you can see that it's going to be 0. This is equal to 0, right? Why? So remember that we are using this condition, under this condition, right? So you see, it's because yes, this is also 0, right? Because the base P expansion of n minus k will actually just be P naught minus C naught. So for n minus k, the base P expansion will just be this, because of that nice condition. Yeah, there will be P and so on, right? Because of that condition, the base P expansion of n minus k will also be this nice thing. And that's why this is 0. Sum of the digits just add sum of the digits of this, which is B naught minus C naught, this plus this and so on, plus the CRs is equal to, of course, the BIs. Fine. So the point that Aditya initially mentioned, that so that kind of so that allows us to take care of one case, you could say. Not really take care, but we actually know that both are not 0 mod P. Yes. But we are not able to, of course, say what is it modulo P. Both sides are not equal to 0 mod P. No, and then LHS is also not equal to 0 mod P, right? Because the valuation is coming out to be 0 for the LHS. That's the thing. Both are not equal to 0 mod P. But yeah, yes, exactly. I know. Yeah. So we know that both are have something, but they are both are not in the local ring ZP. I mean, they are not in the maximal ideal of the local ring ZP. That we know, but we still have to prove that the distance is even. We want to comment on the geometry. That we don't know. We have commented on the algebra that they are both invertible in ZP, right? But we are not able to comment on the geometry. That's why geometry is more difficult, maybe. But yeah, this is the problem which we have to do by group actions. Please imagine, I'm not able to imagine how to apply group actions. And by the way, if you, I think from here, the other case is actually proved, right? That if Bi is less than Ci for some I, then it implies that LHS is 0 mod P. Because geometry implies algebra. Kind of, right? Because you see, if you take this thing, then when you do the base P expansion, you can show that the valuation is you can show that the valuation uh, will be non-zero, will be positive by the same process, because right, the difference will be negative, so there will be some carryover, so the sum of the digits will be less, right? So this is the claim, and this I'm not going to do. You should do it later, but that's the upshot. We have done one side. Claim is that if Bi is less than Ci for some I, then the claim is by the same process. If you do, claim is that SPN minus SPN minus K. And this just be an elementary analysis of carryovers and so on, which you have to do. So you should sit and do that. Sorry, this is positive. This claim cannot be wrong, certainly, because you know that the n wala things cancel out. That's why that formula is nice. Only the sum of the digits remaining. And for the first, you can just reason, right? The first place where that happens, there will be a carryover, right? And that will offset the number of digits. Is it fine? Right? And once it offsets, you know that it's going to be, it cannot be negative because it's a valuation. It cannot be negative. These are not rational. No, these are all, this is going, because n choose k is an integer, it's not a rational. It's just pure integer. So you know it cannot be negative. So if there is an offset, you know who's going to win. So it's going to be positive. You have to do a small analysis you have to do. Okay. So this case is done. Okay. So this formula has some power, but now it will not help us anymore, I think. It will not help us anymore. Yeah, right. So both of them are divisible by P, which, as I was saying, it implies, so that's a geometrical fact, right? That since both of them are divisible by P means that the difference is divisible by P. So geometrically, the difference is less than 1 by P in the p-adic metric, if you know that language, right? But that means that both are invertible, both are in the maximum, not in the maximal ideal, or both are in the maximal ideal. So it implies algebra. But that is not, I mean, yeah, it came to my mind through something there, but it's not needed. Okay. So because you see ZP, we'll talk about that later. ZP is a local ring, right? So I'm using the things like that from there. But we'll get there because it's not useful to solve the problem. But I will can talk about it after we solve the problem. Okay. Yeah. So this is basically a question of p-adic metric, right? You are basically saying that the distance between this number and this number is less than 1 by p in the p-adic system. If you can bring in tools from there and solve it's so, but let's go to the next page. Okay, assume just writing the question again. And we should remember that we know that these two things are invertible. Now, if you think of, we know that they are both non-zero modulo p. Just want, I feel now it should not be difficult. Vaishnavi, if you want, you can go to that section or whatever, wherever the problem is, and maybe you'll get some idea from there what tools and you can suggest us if you think that something you want to do. But now it should not be difficult because now the upshot now is that now we know that the expansions are nice in the sense that the expansion of n minus k is also nice, right? So now it should not be difficult to actually compute this modulo p. But yeah, and I'm sure that using group actions, there will be one solution. We kind of have two cases, and there it will be like directly, I think that we should imagine better. So we have this habit, right? I'm thinking, okay, I can do it by elementary number theory. So that's why I'm not imagining, maybe. Okay. Like the last case, we somehow squeezed in some elementary number theory and did. It's a bad habit, I suppose. Let's compute this. Come on, give some ideas. Yeah, so you see, I mean, we see that this Lucas theorem is essentially a nice way to compute n choose k modulo p, right? By going digit wise. Yeah. I have seen this question theorem in the past. Yeah, now I think I can recall, but I've never proved it. So today we will prove it. It's a fantastic theorem, isn't it? Right? Well, at least it looks very it may have limited scope or whatever, whatever. It depends on how much we can imagine. It looks fantastic. There are similar theorems like this Wolstenholme identity, and I know that those can be proved using these finite field things and so on. This one I maybe lots of Wilson's can help, right? Lots of applications of Wilson's theorem can help us to prove Lucas theorem. I don't know. Maybe they were friends. Yes. Wait. I think I understand what you're saying. Sn acting on subsets of K, and from here you are saying that you will get some alternate formula for the binomial expansion. Okay, cool, nice. Okay. Yeah, I would have not thought of it. Maybe. Okay. No, so let's use that much light, you know, to now let's try to imagine. Yeah. So Aritra, is it see what she is the hint kind of saying, right? That you have Sn, so you are taking this set, which is basically subsets of, sorry, I actually wrote it wrong there, subsets of n of size k. Okay. And it is acting by just permutation. So I'll just write an example. So suppose the subset is 1 to till k, then sigma dot this subset will be the subset. And these are the kind of, you could say, tricks that I also used to prove the Silo theorem. Might be wrong. While proving Silo's theorem, right? Yeah. Hustin has proofs like that. I don't know which book is that, but okay. But yeah, it's probably not Hustin's proof, so it's yeah. So this is the action, okay? This is the action. And then we of course use the orbit stabilizer formula, which says that the size of the group by size of the stabilizer. This is, of course, a transitive action. It's not, yeah, let me just say what needs to be said. So it's a transitive action. And so this is the size of the set on which it's acting. So basically, this gives us the n choose, this tells us that n choose k is equal to size of Sn as the group. And what is the stabilizer? Stabilizer of the set will be those permutations. So, I mean, take x to be this. Can I just leave that the stabilizer has this size? Because you just take 1 to k. Can anyone explain? Yeah, yeah. Yes, yes. Vaishnavi, say if you have. Right, exactly. Yeah, right, exactly. So you need those permutations which take this 1 to k subset to itself, right? Not pointwise fixed, but to itself. So that's k factorial, and the rest means are free sort of. So that's again n minus k factorial. So these many permutations do it. So we get this formula. Wonderful. Okay. So yeah, so we get our high school formula back once again. But how does it help us to do the problem? Oh yeah, yeah. You could. No, it's not Sn minus k. It's cardinality of Sk by cardinality of those permutations which fix and so on, which we just said, which is this cardinality of this. Okay. It's not cardinality of S of n minus k. Yeah. You can, if you think about this will work out. But how to use this? That is the question. So you have to use orbit stabilizer to get modulo p. So the number of orbits, yeah, I mean, and if someone has a direct proof, please tell. Okay, we are just doing any proof will do. So one thing that I can say is that the RHS is also going to count the number of orbits, right? But in a slightly different way. Okay. And it will be something like, there will be something like orbits, 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 and many, many orbits, like the class number kind of thing. And one of the orbits is going to be this, and the other orbits are going to be have size divisible by p, right? Then this will follow. And I think it should follow like this. It should come like this. I mean, I've just taken one step back. It's not doesn't solve the problem. Yeah. Is that idea okay? Yeah. Or please tell me. then only you will get that mod p, they will vanish, right? Correct. So you have to consider the action of Sn on these subsets in a slightly different way. In the action, yeah, you may even consider a different action, or you may partition this and something. But yeah, you have to get that kind of thing, that the orbits. You may even consider a different action because the number of orbits do not change. Yeah, maybe 5 more minutes and then we'll have to look at some solution, because, or if you people think that we should think about this, then you can think and we will not look at solutions. Yeah, you see, so far we have not used the digits and so on, so we should use that. How else can Sn act? Precisely C naught. and think how else to partition and what action to take. There should be something very natural. Yes. So at the moment, we are trying to just do the proof by group actions. I do believe that a direct proof is possible, but let's focus on proving it using escape, right? Something is there and just escaping. Should we should be able to understand what it is. Can't just escape. What do you think? Any ideas? You see, this is the kind of split that we want, right? But the whole point is that we should not means we cannot. I mean, we want group actions to we want to define a wise action kind of for this situation so that this automatically happens, right? Then only we'll be using group actions, right? Orbit stabilizer. So we have to change the action, you see, right? So that this automatically happens. Or maybe these actually might be all orbits of size 1. These many orbits of size 1. That's the other situation, right? Where this kind of thing happens. Do you see my point? Yeah, right. I mean, it probably is not useful, but just telling you what I see. So you see, I'm putting the effort, but I'm not able to, not putting the effort in imagining, not able to do that. You see, that's where the problem is, right? Means we have to consider the digits, right? And we have to somehow use that in in the definition of our action. The digital expansion we have to use. So this means a subset of size C naught from B naught. What kind of numbers is encoded here? Yeah, maybe I will think about it tomorrow, right? S- s- Yeah. Okay, yeah, because I think right now I'm not getting any ideas. Yeah, better to, yeah, think about it tomorrow. So let me think. I mean, because I think thinking and putting more effort is more useful, right? Because I don't see the way. If I saw the way, and if I would understand that, okay, now it can be done, then I would. But here there is some idea waiting, right? So let me try to see it, and then of course we can. It's a theorem, so it will be there somewhere. Why don't you also think, right? You can try to think, and you may also try to think along the lines of a direct proof, right? Direct expansion and directly computing it modulo p, right? Taking that way also, you maybe, so you understand, you take the n factorial, you have the expansion, and then you decrease and you try to reduce it modulo p, use Wilson's theorem, when you have p minus 1 factorial, that's minus 1, things like that you can try to use. Okay, so yeah, see, I mean, at least we know that both sides are both sides are non-zero. That much we know, which is a nice thing. But you see, this is more precise information. Okay, so yeah, let me stop here. And about Tuesday, I will let you know. I plan to take a class on Tuesday. Okay, yeah, is that fine? Yeah, I'm seeing because. Yeah, I might have to take it in the evening. Is evening also fine with you, just in case, or just don't know, tell me, or you can tell me later also. If morning is okay, okay, and evening might not be okay. All right, then I will try to keep it in the morning only. Okay, because there was one person, so she's having, because she's in a different time zone, and she also missed one class, and yeah, to also accommodate, but. Let's see. So evening is not going to work. Maybe only for one class. So evening will not work, right? Yeah. Yes. Will it work or okay? Yeah. Just let me know whenever possible. And I also do want to do in the morning only. So that's maybe one class because she missed 1 week also. So anyways, yeah. You tell me if that is possible, and I will tell you. I'll try to keep it morning, and then I will. If not, then I will let you. Okay. Yeah, yeah, we'll see. But think about this problem and also the field theory. So next class we'll do field theory. We'll do this and then we'll do. So try those Galois theory questions. Mostly it's not Galois theory, it's just automorphisms. Okay. But try and if you get stuck, then you try to find out, right? And but try and do some problems because we want to make sure that we keep moving forward. Yeah. Okay. So okay. Good.